Hello, today I'm going to be talking about a problem regarding performance. And if you remember, we had three different components of performance. If we wanted to find the execution time of a program, that would be the number of instructions in the program, the cycle time, and the cycles per instruction. And that last part, the cycles per instruction, may be given to you in the problem, but in this particular problem we're going to have to calculate it. Calculating the CPI for this problem is not all that hard because it only consists of two different types of instruction. But if you have more than two different types of instructions, we just use that weighted average method. So let's begin on this one. We have a program. There's 5,000 floating point instructions, 25,000 integer instructions. Has a clock rate of 2 gigahertz. We're calling this one processor A. We'll see processor B a bit later. And we also have the CPI for the individual types of instructions. So 7 cycles per instruction for floating point, and then integer instructions take 1 cycle. The question is, how long does it take for this processor to run the program? Now we could calculate the average CPI, but we can also realize that if we have the cycle time and the number of cycles, we multiply those together directly and we can get the time. So let's try it in that way. First of all, we say, all right, we've got 5,000 floating point instructions, and each of those takes 7 cycles. How many cycles for the floating point? Well, we multiply those together. So for the cycles for the floating point, that's going to be 7 cycles, and there's 5,000 instructions. So that's going to be then 35,000 cycles just for floating point. And then how many cycles do we have for the integers? Well, there's 25,000 of them, but they only take 1 cycle each time. So the cycles for the floating point, 35,000, gets added to the cycles for an integer, and that's going to be 25,000 cycles. So together, that's going to be 60,000 cycles. That's ticks of the clock. Then we have to find out how long does each cycle take. We could directly divide by the frequency, but let's flesh that out a little bit. Cycle time is going to be 1 over the frequency. Because the frequency gives us how many ticks we have in 1 second, we want to know how long each individual tick takes. So that's going to be 1 over 2 times 10 to the 9th hertz. Remember, hertz is 1 over seconds. And so that's going to give us with 500 picoseconds. Now we multiply these two numbers together. So these numbers together, we have 500 picoseconds and 60,000 cycles. When we multiply these together, we get 30 microseconds. And that's the answer to the first part. What's the average CPI for this processor? Well, there's 2 ways to do it. One way is to find the percentage of each type and use the weighted average method. So what's the percentage of floating point? Well, the percentage of floating point, and I'm going to drop the 1,000 here. So there's 5,000 divided by 5,000 plus 25,000. There are 30,000 total instructions, and that gives us 16.7% floating point. And then the remaining integer instructions are 25 divided by 5 plus 25, or 30,000 total instructions, and we get 83.3% integer instructions. Okay? So then what we do is we multiply. We know that 16% take 7 cycles, 83% take 1 cycle. We take the weighted average method. So 16% take 7 cycles, and then 83%, it's a 0 here, take 1 cycle, and that gives us a weighted average of 2. What would be another way to solve this? Well, we could say how many total cycles are there and how many total instructions. If we look up to the top, remember we had 60,000 cycles in the whole program. Then how many instructions did we have? Well, we had 5,000 plus 2,500. There were 30,000 instruction. So since we're looking for CPI, or cycles per instruction, we got our units right here. We had 60,000 cycles, we had 30,000 instructions, so that in the same way yields 2 cycles per instruction. So we can do it either way. The weighted average method works well when we have several different types of instructions. This works well for this particular problem because we had already calculated those things. So we're going to move up here, and I'm going to move over. So with this, we've got still dealing with processor A, and so we've got a new program. Before we were talking about program 1, now we're talking about program 2. Remember, for this program, we had a CPI of 2. But what happens when the instruction mix changes when we run another program? Well, let's look at this program. It has 100,000 floating point instructions and only 50,000 integer instructions. So we'd say to ourselves, oh, that's bad news. We have expensive floating point instructions, and many of them, and we have only a few of the cheaper instructions. What's the average CPI? Well, we can do that again. We could say that so when we look at the mix here, there's 150,000 total. So we have 100,000 divided by 150,000. You can see that 2/3 of them are floating point and 2/3 of them are integer. So we have 2/3 floating point and we have 1/3 integer instructions. Well, we can use that directly, so we can say 2/3 times the 7 plus 1/3 times the 1 is going to equal 5 cycles per instruction. 5 cycles per instruction, using that method. Hopefully, we'll get the same answer when we try it using method 2. When we think, how many total cycles do we have? Well, there's 100,000 floating point instructions, each taking 7 cycles. There's 700,000 floating point cycles. And then we have 50,000 integer cycles. And together, that's 750,000 cycles. For this particular program, well, we had 150,000 instructions. So to find the CPI, we divide the number of cycles and by the number of instructions, that's cycles per instruction. So we have 750,000 divided by 150,000, and that equals 5 cycles per instruction. 5 cycles per instruction. Now we're going to take a look at a new processor, processor B. Processor B, now, we're given the CPI directly for this particular program, for program 2. Now the CPI would probably change if we had a different mix of instructions in, let's say, program 1 or program 3. So we have an average CPI of 3.5, clock rate of 1.8 gigahertz. How much time does it take to execute? Now we need those 3 things. We need number of instructions, cycles per instruction, and clock cycle time. Here we don't have the number of instructions explicitly stated. However, we do know how many instructions there were. There were 150,000 instructions, and they were mixed between different types. So they had to, this is given in the program, the 3.5 cycles per instruction. Somebody had to have calculated that, and it's just given in the problem. But realize it's only valid for program 2. So we've got the three legs. We've got the number of instructions times the CPI times the cycle time. And that product will give us our answer. So we have 150,000 instructions, and then we have 3.5 cycles per instruction. And what's the cycle time? Well, we're given the frequency, so we have to take 1 over 1.8 times 10 to the 9th, and that's in hertz. And this gives us our cycle time. We find out that the product is 292 microseconds. We say which processor is faster and how much. Okay, well, we know the time for processor B. We haven't really calculated the time for processor A, though, explicitly. So if we say time A, that's going to be, remember, the number of instructions is still 150,000. And then we calculated that it was 5 cycles per instruction. And then we can't use B's clock rate. Remember, time A, we have to go all the way back up, and we saw that it was 2 gigahertz. So we have to use 2 gigahertz in our calculation here. So it's be 1 over 2 times 10 to the 9th. So that's 2 gigahertz, 1 over 2 gigahertz. And that's going to be 375 microseconds. All right, so we've got 3 things to fill in the blank here. Which processor is faster and how much? Well, let's look. A takes 375 microseconds, B takes 292. The alligator eats the bigger number, and we say, oh, A is a bigger time. That means it's the worst performance. We want things to execute in smaller time, so that means that processor B is faster than A. That's the first thing we fill out. And then we need to calculate what the ratio is. The ratio here is just going to be 375 microseconds divided by 292 microseconds, and that ends up being a ratio of 1.29. And it's unitless because we have microseconds divided by microseconds. And then remember that A, the time of the worst processor, has to go in the numerator because this number always has to be greater than or equal to 1. So that's the problem as we have it. Make sure to comment on the video, and thanks for watching.